Hi, good afternoon, everyone. Today I'm going to talk about some of the challenges I have had on fabricating cortisol immunosensors on gold screen printed electrodes. So first, I'm going to go through why we are interested in measuring cortisol, why cortisol is an um, important biomarker. So cortisol is most commonly known as the stress hormone, which itself gives us why it's important, I think, because stress impacts both our mental and physical well-being. And also cortisol is involved in a multitude of processes in the body, including cardiovascular, renal, skeletal, endocrine systems. Cortisol also follows a circadian rhythm in the body. The levels follow a circadian rhythm, meaning it's highest in the morning and lowest in the evening. And because the levels vary throughout the day, it is important to measure, to get multiple measurements throughout the day in order to get like useful information out of it. Or it's the levels are also affected by things like your genes, your environment, and also your daily social and emotional experiences. And because of these factors, in order to get a better picture of whether your cortisol levels are normal or abnormal, you need multiple measurements throughout the day. So what are the limitations of the currently available commercial measurement techniques in order to do this? So currently what's being used is high performance liquid chromatography, HPLC, or ELISA, or even chemiluminescence immunoassay, which all require laboratory equipment and also dedicated space, trained personnel, and also some labeling steps. So what's the alternative? It's electrochemical sensing, which gives us the advantage of real-time measurement. So we recently did a systematic review on the currently existing electrochemical cortisol sensors, and we observed that there are three main different categories based on like the kind of bioreceptor that's being used to recognize and capture cortisol. So one of them is antibodies, which 34 out of the 61 papers we noticed were use antibodies. The next one is aptamers, which are single-stranded nucleic acid molecules that are made specific to capture cortisol. And the third one were molecularly imprinted polymers or MIPS, which are polymer films that have a negative space or holes that are complementary to cortisol. Out of all these, antibodies are the most well-researched. And for this reason, and also because antibodies and aptamers are the most well-researched, and well, aptamers and molecular imprinted polymers, MIPS, have actually shown advantage of, in the literature, stability, advantages over antibodies for stability. While MIPS, in the literature and also certain colleagues I have spoken to have mentioned about reproducibility issues. So for my project, I decided to work with antibodies and aptamers for now. So first I wanted to work with antibodies, and for cortisol immunosensors, which uses antibodies, how are this cortisol quantified in these immunosensors? So the thing about cortisol is that it doesn't have a redox center, which means it can't undergo reduction or oxidation, giving us any information about the current. So if we are going to use a Faraday process to quantify cortisol, we need an external redox mediator. So how this works is that when there's no cortisol bound to it, there's no hindrance to the transfer of the redox probe to the electrode surface, meaning it should give us the maximum current. And the more cortisol we have, the more hindrance there's for the mass tunneling of the redox probe to the electrode and also in the electron exchange, which means the more cortisol we have, the less current it should give. So from the literature review, in the cortisol immunosensors, the most widely used electrode-based material for cortisol immunosensors was gold, and the most widely used redox probe was potassium ferriferous solution in PBS. Which was curious because there's also other literature, other studies, which shows that these two combination of this electrode-electrolyte is a problematic combination. So during our cortisol immunosensor measurements, we also wanted to see if there's any impact, additional impact of this. So we fabricated the cortisol immunosensors from recipes we found in the literature already, where we have a gold electrode, a cross-linker to immobilize the antibody, and then we are blocking the unbound surfaces with ethanolamine. And we characterize the stepwise fabrication by running CV after each step. So with each layer, we expect that there will be more insulation. That means there will be less current. So this is when we did CV, and after each modification layer, there's a decrease in current as we expected. And this showed us that, okay, there's the layer deposition and the sensor fabrication actually went well. Then we did the evaluation of the sensor performance, which was done in the redox solution, which is ferriferocyanide solution in PBS, where we spiked the ferriferocyanide solution with increasing cortisol concentration. And as you can see here, this is what we expect. There's a decrease in current with increase in cortisol concentration, which is great. I was happy with that. And we have approximately, we can see that there's a 42% decrease up until 1 nanogram per milliliter. But this happened. There's an increase in current after a while, and I wasn't sure why at this point. So this wasn't great. This was unexpected for me. From other studies that I looked up, I hypothesized that, okay, some of the factors that can be affecting impacting these results can be the absorption of chloride ions from PBS, or the absorption of ferriferocyanide ions itself. And the zone 2, or the increase in current, probably is due to etching of gold surface or the removal or instability of the monolayer itself. So in addition to this, I also ran a control experiment where the sensors fabricated the same way on the same day. I put it in ferriferocyanide solution and did it. This is without cortisol. I can still see a decrease, like about 17%. And it also followed the same trend. So this is with no cortisol, the same type of sensor. I can see the same trend as with cortisol. So we can see that out of 17% out of the 42% of variations is not due to cortisol at all, because this doesn't have cortisol, which means that about 40% change is due to compounding effects here. And the existence of zone 2 in both these graphs in the test and the control indicates the removal of material from the sensor or sensor etching. So we wanted to test this hypothesis. These three hypotheses, and see which how they are affecting the sensor performance. So in order to do this, first here we tested gold screen printed electrodes, where we capped them in PBS and in sodium sulfate, 2 different tests, and did incubated for 15 minutes and ran DPV, or differential pulse photometry, in ferriferocyanide. And you can see that in PBS, there's a much steeper decline than in sodium sulfate. So in PBS, it has chloride ions. In sodium sulfate is a chloride-free buffer. So the presence of chloride and the absorption of chloride onto the gold surface does impact the electrochemical sensor measurements here. We also did on quartz crystal microbalance with dissipation, or QCMD test here on a gold sensor. So for QCMD, the Sauer-Bray equation says that the frequency changes are inversely proportional to the mass changes on top of the sensor. And so we did 2 sensors, two QCMD gold sensors, where one for the control we've just flown PBS over, the other one we did with ferriferocyanide. And here we can see the green line is the ferriferocyanide, and we can see there's an increase in change in frequency, which means that there's a decrease in mass. This is just a gold-based sensor. If there's a decrease in mass, that means that gold is being removed. So this shows us that, okay, this combination also leads to cyanide-mediated etching of the gold surface, which is another factor that's impacting the results. The third one is for the third test, we did, again, gold screen printed electrodes, where we capped the electrodes in ferriferocyanide solution, one in ferriferocyanide solution and one out of the solution, and where we did We incubated for 30 minutes and again ran DPV experiments in regular intervals. So the one in the ferricyanide solution or the redox solution shows us that there's a about 40% decrease, while the one out did not have that much of a decrease. This shows the actual combination effect of both adsorption of both chloride and ferricyanide ions in the measurement of the electrochemical measurements. Oh. We found out that these three there are three main factors here impacting, causing false sensitivities also, and also impacting the results for the electrochemical sensing in these cortisol immunosensors. And that is adsorption of ferricyanide ions, and adsorption of chloride ions, and possible removal of self-assembled monolayer and cyanide etching of gold surfaces. Our suggestions, or what we noticed, was that it is very important to reduce the amount of contact. I don't think it's possible at this point to eliminate all the effects of this, but to reduce the amount of the time sensors stay in contact with the redox or buffer solutions, and if possible, use a single sensor for measurement instead of doing all the calibration on one sensor. And very, very, very importantly, to run control experiments to ensure that the changes you are seeing are due to the binding effects you wish to quantify and not other effects. Yeah, that's it. Thank you.